Okay, we're going to take a look at problem 46 from chapter 38 of the fourth edition of Knight's Physics for Scientists and Engineers. This is a problem that combines Compton scattering with a couple basic results from special relativity. So in a moment, I'll draw a little diagram of the scattering event itself, and then we'll go back and talk about rest mass in special relativity. In this problem, we have not an X-ray photon, but a high-energy gamma-ray photon. Remember, visible light photons have 2 or 3 electron. What is this? Get out of my face. Go away, please. Okay. Visible light photons have 2 or 3 evolts of energy. Gamma-ray photons, look at this, 350,000 evolts, so way more energetic than a visible light photon. And this incident gamma-ray photon scatters off of an electron, a free electron. And some of that energy is going to be absorbed by the electron. The rest of it will continue on in another photon. And we can say the same thing about momentum. The free electron was just sitting there, supposedly, not moving, having no kinetic energy, but after, I should say no momentum, but after it interacts with the photon, it will also have momentum. So we're going to regard the photon and the electron as colliding like two particles, just like two billiard balls on a pool table. And using the physics that's been developed in the chapter, we're supposed to figure out afterwards what's the electron's velocity. And before we get into it, I want to point out, if you do some Googling, there's some great information on the web. I can post this on Canvas about or surrounding the fact that a free electron cannot fully absorb the energy of an incoming photon. Some of the energy has to be carried off by the scattered photon. And the reason it's impossible is because it turns out you can't simultaneously conserve simultaneously conserve energy and momentum in such a collision. But this problem is not about full absorption. Some of the energy is retained by the photon, and then some of it is given to the electron. So function F11, how do I get out of here? And let's go to OneNote. Let me draw some stuff very crudely. Emphasis on crudely. All right, here's my electron just sitting there. Don't be misled into thinking that an electron is an actual little ball of mass. It's more like a wave of probability. We were supposed to confirm that in our electron diffraction lab. Here comes the incident photon, which I'll draw as a squiggle. It's a real squiggly squiggle because it's got very high energy, and that means a short wavelength. So the energy incident, E or initial, is 350 kiloevolts. Not killa as in K-I-L-L-A, kiloevolts. And once it strikes the electron, this photon will be scattered off at some angle, and I'm going to purposely draw it with a slower squiggle, which means a longer wavelength, which means a less energetic photon. We know that longer wavelengths for light correspond to lower frequencies, and low frequency photons have less energy than high frequency photons. So let me just draw a dashed line indicating the original direction of the incident photon. And I believe your book likes to use the Greek letter theta for the angle that the photon's exit velocity makes with the incoming velocity. Now, before we look at the formula, and I'm not going to derive the formula for Compton scattering here. Let me just go ahead and write it down right now. We've got some incident wavelength, or initial wavelength, lambda initial, and then a final wavelength, lambda final. We know that lambda final is going to be longer than lambda initial, and here is the amount of increase, delta lambda. And these numbers often come out in picometers. If you're talking about scattering of photons off of electrons, typically the shift in wavelength is on the order of picometers. If this thing was a much more massive proton, and that problem doesn't usually get treated. I did some Googling, and it's because the proton has internal structure, so analyzing the collision can be more complicated. But the shift in wavelength there is negligible compared to the shift for an electron. It would be like on the order of femtometers or even smaller. So usually it only makes sense to talk about Compton scattering off of a very light particle like an electron. In any case, here's the formula. It's Planck's constant divided by mc. mc. I think this is called the Compton wavelength of the electron. Compton wavelength, lambda sub c. And the reason for that is, you'll recall up here that for a material particle or for a photon, wavelength is Planck's constant divided by momentum. Well, if the electron were going at the speed of light, then classically, this is not actually accurate, but classically its momentum would be mc. So this quantity classically, well, a mix of classically and primitive quantum theory here, this would be the wavelength of an electron going at the speed of light. Of course, we know an electron can't actually go at the speed of light, but that helps you recognize this quantity, and instead of seeing three unrelated numbers, you can think of it as one physically meaningful number, times the quantity 1 minus the cosine of theta. And we can draw a graph of this real quick for Compton scattering. Let me draw some axes here. All right, vertically I'm plotting the shift in the wavelength, and horizontally I'm plotting theta. I don't want to clutter this diagram, so let me just narrate the various manipulations we're doing of the cosine function, and then I'll draw the final result. So we start with cosine, and let me just trace out what that looks like. You all know that cosine goes like this, right? Between 0 and 180 degrees, it dips down and then ends at -1. But we've got this minus sign out front that would flip the whole thing across the theta axis. So instead of starting at 1 and dipping down, it's going to start at -1 and scoop up. See that? So negative cosine starts at -1 down here and then scoops up. I really hope you can see my little cursor here. But then we shift the whole thing up by 1. So instead of starting at -1, we start at 0 and scoop up. So this is really what 1 minus cosine theta looks like. Something, you know what, can I do a Control Z? Yeah, I think I can do a better job with that. There we go. That's what 1 minus cosine looks like. And check it out. This would be the value of 1, but we've scaled it by the Compton wavelength. So imagine this incoming photon is barely influenced at all by the electron, and that theta is small. So the photon just gets deflected a tiny little amount, like that. That's a small value of theta, so when you look at the graph, that suggests a small shift in wavelength. But for 180 degrees, I should probably emphasize, oh, that's pretty sloppy here. Can I do a better job than that? No. This is at 180 degrees, which would be a complete reversal of direction. The photon gets bounced right back from whence it came. That's when there's the very largest shift in in the wavelength. Not the Compton wavelength, but the actual wavelength of the photon. Not surprising, right? You would expect that when the photon's bounced straight back from which it came, that's the greatest possible change in its energy and momentum, and hence its wavelength. So let's think about momentum and energy here. Note that the incoming photon, let's imagine this is the x-axis for concreteness. If the photon is moving along the x-axis before the collision, it has no momentum in the y direction, 0. And yet, after the deflection, if the photon's going this way after the collision, then it would have a component of momentum in the y direction. It would have a positive component of y momentum. And we know from conservation of energy that if we started out with 0 y momentum, as we did, then we must end with 0 y momentum. So in order to compensate for the for the photon's positive y momentum after the collision, the electron would have to acquire a negative y momentum. And that's why we can pretty easily see that the electron has to do something like this. It's got to move down at some other angle. I could call that phi, so that the electron has a negative component of y momentum, in order that the total y momentum still be 0. Okay, well, if the electron goes from not moving to moving, clearly the electron has now acquired kinetic energy. Where does it get that energy from? It came from the energy of the incident photon. So just by using conservation of momentum, we've already concluded that deflecting the photon from its initial direction necessitates an exchange of energy and momentum. And if you apply the conservation of energy and momentum principles to this collision, and you use a little bit of relativistic mechanics, you arrive at this result. I don't remember if your book actually shows you all the gory details. It's not that bad, but it takes a little bit of time. So that's the Compton scattering formula. And now we need to go back and talk about the rest energy of a material particle in special relativity. Here's a real nice picture of our star, the sun, taken by the Solar Dynamics Observatory, which I think orbits the sun at the same distance planet Earth orbits the sun. Oops, getting ahead of myself. And for a long time, physicists, other scientists, people in general, must have conjectured, or did conjecture, about the source of the tremendous amount of energy that the sun releases. It wasn't until fairly recently in history that we had some idea of just how old the solar system is. It's billions of years old. People may have at one time thought millions of years or even less. But once scientists started to get a sense of just how old the sun is, it begged the question, where is this energy coming from? It's such a vast quantity of energy, especially when you look at how far planet Earth is from the sun. We intercept just a tiny sliver of the total power being radiated by the sun. One of the early conjectures was that as the sun contracts towards its center due to gravity, that some of the gravitational potential energy is then transformed into kinetic energy of the particles within the sun. So you get those particles really hot, and they shine brightly, just like the coils in a toaster oven. But before too long, when scientists begin to study just how much energy is available because of that gravitational potential energy and the amount by which the sun might contract, it didn't at all account for how much energy has been pouring out of the sun for billions of years. So according to the brief reading I've done, we'll come back to the slide, this guy was the first person to accurately suggest the source of the energy. Now, this formula here, E equals mc squared, that's due to Einstein in the that would be around 1905. But several years or a decade or two later, Sir Arthur Eddington is the one that suggested that perhaps the conversion of matter itself into energy is the source of the sun's power. So this is a formula that we're going to need to solve this problem. Perhaps to motivate that formula, we can just talk about what's actually happening in the core of the sun. Now, the details are more complicated than this slide suggests. There are a variety of reactions that have to happen in this sequence called a chain, and there are actually separate chains that have the same result. But here is the result, the net result. Inside the core of the sun, there is a great deal of hydrogen gas, hydrogen particles. I guess it would be a plasma because it's so hot that everything's ionized. So a bunch of just bare protons flying around. You could think of a proton as the nucleus of a hydrogen atom. Now I'm using a system of units here that I just made up for convenience. But in this system of units, where's my pointer here? Laser pointer. Yeah. Let's assign each of these protons a mass of 75. So obviously that's not kilograms or grams or any other unit that you're familiar with. But if the mass of each of these protons is 75, then during this rather complicated process at the core of the sun that combines those 4 protons into a helium nucleus, and obviously that requires the conversion of 2 of these protons into neutrons, So we still have 4 nucleons overall, but now 2 of them are 2 of them are protons and 2 of them are neutrons. In that process, some of the mass is actually lost. And these numbers are pretty accurate. So whereas you would expect the 4 protons together to have a combined mass in the helium nucleus of 300, 75 times 4 is 300, they actually have a combined mass of 298 once they're fused into a helium nucleus. So some of that mass seems to be unaccounted for. Where did it go? Where did those 2 out of 300 units of mass go? Pure energy is the idea. Energy in the form of kinetic energy, but also light. Both of those things is where that energy winds up. And of course, ultimately, the light energy is what travels for 8 minutes from the surface of the sun to the surface of the earth. And that's what powers just about everything that goes on here on planet Earth. The plants absorb that sunlight. Animals eat the plants. We eat the animals. Well, some of us do. And we burn the fossil fuels that came from the plants, collecting the light for millions of years. That's where it all comes from. It all comes down to this process. Like I said, the details are more complicated, so in a moment I'll show you a graphic from a Wikipedia page that has a ton of information about the so-called proton-proton chain, but this is the net result. This guy hadn't worked out the details at the time, but from what I've read, he was the first to correctly assert that it's the conversion of mass into these other forms of energy that is responsible for the sun's tremendous power output. And then this guy came along, I think 1939, Hans Bethe, and he actually worked out the details of the calculations. So much of what you can read about on Wikipedia in the regarding the proton-proton chain, which is the sequence of reactions happening at the core of the sun, was originally worked out by this guy. And you can see the calculations were so intense that his deep thinking generated quite a bit of steam that kind of expanded his head. You know, the steam had nowhere to go. Okay, let's look at the decrease in mass of that system of 4 protons. I asserted that 2 out of 300 of the mass just disappeared. Well, we know it didn't disappear. It was transformed into kinetic energy, light energy. Well, this is the ratio, but the actual mass in kilograms would be 4 times the mass of each proton, and this is about the mass of a proton. So the quantity of mass that was vanished, so to speak, is this number right here. Now, that's less than the mass of 1 proton. We know that the mass of a proton is about this much right here. So this is almost 2 orders of magnitude less. So it's a tiny quantity of mass that's been transformed into energy, but with great consequence. Because if you go back to the formula that we've all heard about, mc squared, sure, you're taking a very small number to represent the mass, but you're multiplying it by a very large number, depending on your system of units. And if we're measuring distance in meters and time in seconds, c is the number 3 times 10 to the 8th. C squared, well, the 3 squared gives us a 9, which is basically 10. 10 to the 8th squared is 10 to the 16th. Add in that other factor of 10 from the 3 squared, and you're looking at basically 10 to the 17th. Huge number times a small number can still give you a substantial number. So let's do that conversion. If E equals mc squared, then the change in energy, or the energy liberated, will be the change in mass times c squared. Just take this number, multiply by the square of the speed of light, and you find, what is this, 4, what's the prefix, 10 to the negative 12th pico? 4 picojoules of energy are released. Doesn't sound like much, but again, we're just talking about the combination of 4 individual protons into a helium nucleus. That's a tiny little system. And you can imagine, because the sun is so massive, 99.9% of all the matter in our solar system is locked up in the sun. So there's an ungodly amount of hydrogen particles or protons at the core, and if even a small fraction of those are fusing every second, that's an enormous number times this teensy number ends up still being an enormous amount of energy released. Anyway, enough talking. Let's convert this into mega evolts. You guys know how to convert from joules into evolts, you divide by 10 to the negative 19th, basically, and then you would divide again by 1,000,000 to convert into mega evolts. So memorize this number just for now, because it'll show up again in a moment. But 25 million evolts is the amount of energy that we get from one of these proton chain sequences. Silly graphic here of the sun cut open like a peach, so we can visualize the core, where the fusion is actually happening. And I believe right now the sun is only fusing hydrogen into helium. Later, towards the end of its life, billions of years from now, it will also fuse the helium into heavier elements, maybe carbon. And more massive stars have several layers of fusion going on at once, like an onion. And that's where something like half of the periodic table comes from, maybe even more than half. Here's a more detailed graphic representing the proton-proton chain. And I think in a moment, let me get out of PowerPoint here, and we'll look at the Wikipedia page that shows that number, 25 mega evolts. So how do I get out of here? Function F11, escape. Here's the Wikipedia page. Lots of information here. We don't need to know most of this. But I'm looking for that number, 25 mega evolts. And I probably should have looked it up ahead of time. Here's something that looks... No, that says 25 million kelvins. That's different. Energy release. There we go. The total energy yield of one whole chain is almost 27 mega evolts. So I just used some really rough numbers in the slideshow, but we can see order of magnitude, that's about right. So like I said, there's multiple different pathways that have their overall result of fusing 4 protons into helium. Lots to read about if you're interested. What's really meaningful is to compare that energy output to a typical chemical reaction, like the combustion of one molecule of glucose. So I just did a quick Google search. Somebody who teaches chemistry could make this more precise for you, but if you combust or burn 1 mole of glucose, you get this much energy out of it. Where's my laser pointer? 2,840 kilojoules per mole. Now, there's probably more than one way to liberate that energy. Maybe you could burn it directly, like in a flame, or you do what your body does, which is a more complicated chemical pathway, and it takes longer. You don't want to release... If you eat a pizza, like a Little Caesars pizza, which I'm sure some of you have done, you wouldn't want to release all that energy in your body at once. That would probably explode your body into little bitty pieces. So it's released slowly throughout the day as you move around and lift stuff, throw stuff, pick up your pencil, do your homework. Okay, let's convert this into the number of mega evolts released, or how about evolts? The number of evolts released per molecule. That's just a simple unit conversion. So first we convert kilojoules into joules, multiply by 1,000, and then you convert joules into evolts by dividing by that teensy-weensy number, which is going to give us a really big number. But then lastly, that would be the energy released per mole of glucose. But there are 6 times 10 to the 23rd molecules per mole. So divide down by that enormous number, avocado's number, and we find about 30 evolts are released every time you burn, I'll say, 1 molecule of glucose. 25 to 30 evolts. Contrast that with the 25 mega evolts, million evolts released when 4 protons are fused into a helium nucleus. So a good number to take away with you from this class is that a typical nuclear reaction releases about 1 million times a typical chemical reaction. In a chemical reaction, you're rearranging electrons between atoms. You're not cracking a nucleus in half or smashing 2 nuclei or 4 nuclei together. The nuclei have very little to do with it. It's about rearranging electrons and how they're shared. But in a nuclear reaction, you're actually doing something to the nuclei. And I should point out that even chemical reactions involve a very tiny change in mass, which was not known until after Einstein's theory. But if you were to weigh the glucose and the oxygen before the reaction and then weigh whatever the products are, there's probably carbon dioxide in there, maybe water, I don't know the details, but if you weigh the products after the reaction, you would find a very tiny decrease in mass, just like the decrease in mass that we observe with hydrogen fusion at the core of the sun. But the decrease in mass for a chemical reaction is something like 1,000,000 times less than the decrease in mass for a nuclear reaction. It's all about change in mass and transformation of mass into other forms of energy. Okay, we're back in OneNote here. As you recall from the statement of the problem, the incident photon had a whole lot of energy. And we're going to find from the Compton scattering formula that it also gives up quite a bit of energy. So the recoiling electron, the electron that the photon collides with, is going to have a lot of kinetic energy. That means it's going to be going really fast. And anytime something's going super fast, like 10%, 20%, certainly 40% the speed of light, you can't use 1/2 mv squared for the speed and the energy relation anymore. You have to use a relativistic formula. So here's some other background that we need. First, let's talk about the rest mass of an electron. Hang on a second. We know now that matter, just by virtue of existing, has energy. It could have kinetic energy. Now let me rephrase that. If you could somehow convert the mass of matter into pure energy, this is the relation between the mass and the energy. E equals mc squared. Notice there's no factor of gamma here yet. E equals mc squared. This is the rest mass. We call this the rest energy. So if something is just sitting there, not moving, it still has energy because you could theoretically take all of its mass or even part of its mass and transform that into other forms of energy. So let's calculate the rest mass. Oops, how do I get rid of this? You can see I'm a noob here with this tablet. Rest energy of the electron. Rest energy. Wow, this is really bad. I just got to get in the groove here. As long as you can read it, right? Now, to go from one to the other, to go from rest mass to rest energy, you just multiply by the square of the speed of light, which is trivial. So specifying the rest energy basically is specifying the rest mass and vice versa. I'm going to put a dot, 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 because we're not actually going to do the calculation. I'm going to quote the result because I know it. If you take, 9 times 10 to the negative 31 times 3 times 10 to the 8th squared, you get a tiny number in joules. I say tiny because even though c squared is a huge number, the mass of an electron is really, really small. So it still comes out some large negative power of 10. But convert from joules into evolts, and you get this. It's about, if I recall correctly, 511 kiloevolts, which is interesting because the numbers we're looking at in this problem are in the hundreds of evolts. Right? That's the energy of the incident gamma ray photon. Of course, you could divide that by 1,000 and call it roughly half of a mega evolt. If you think you're going to take more physics classes in the future, I don't know, try to commit that to memory. The rest energy of an electron is something like half of a mega evolt, or 500 kiloevolts. Remember a while back I showed you what I call the energy momentum triangle for relativistic mechanics? Just draw a right triangle, hopefully better than... Ooh. Let's try that again. Nope. I feel like I'm just learning to write here in kindergarten. Alright, good enough. Just in case it's ambiguous, this is a right triangle. The hypotenuse is the total energy. One side is mc squared, and the other side is pc, where p is the relativistic momentum. And I should emphasize that p is no longer just mass times velocity. That's usually not going to work. I purposely drew this side longer because usually for a material particle traveling at everyday speeds, this number is quite a bit bigger than this number. That's why I drew this side of the triangle longer. But you could use Pythagorean theorem to express the total energy of the particle in terms of its rest energy and this quantity here. Now, it's really tempting to do the following, and I heard somebody in class ask about this, which is very, very insightful here, but notice that the energy, total energy, is not merely the sum of mc squared and pc. Oops, yeah, that's correct. That's a 2 right there. It's going to bother me, so let me fix that. Come on. All right. This does not work because this is a right triangle, right? The whole point of drawing this triangle, remember that the triangle is just like a mnemonic device sort of for memorizing the actual relation. E is really the square root of this squared plus this squared. If this were true, if this was an equality, not this equal sign with a line drawn through it, then you could conclude that the total energy is rest energy plus what must be kinetic energy, right? If the equal sign was legit, then the logical conclusion would be, well, the total energy is rest energy plus kinetic energy. This must be the kinetic energy. This is not the kinetic energy because this is not the actual equation. So I'm going to emphasize that capital K is not just PC. That does not work. This equation, or this triangle, allows you to relate the momentum to the energy, but it doesn't easily allow you to relate the kinetic energy to the total energy. So, once again, why does something have energy? Well, it's got mass, and it may also be moving. So think of a baseball. If you could transform the mass of a baseball into pure energy, it would be bigger than the biggest nuclear weapon ever detonated. But if you then throw the baseball before you convert all of its mass into energy, just by throwing the baseball, you give it additional energy that we call kinetic. So how do we get the kinetic energy from the total energy? Well, here's where a new formula comes in. I'm not going to show where it comes from. In fact, off the top of my head, I forget how to get to this result. Pick up any book on special relativity. It's going to walk you through the steps. Even our book will show you some of the background. But here's what you do. In order to quantify the total energy of a massive object in motion, whether it's a tiny little electron or a spaceship flying through interstellar space really fast, so this capital E includes the rest energy. That's the energy it would have if it wasn't moving, just by having mass, but also its additional kinetic energy. You take mc squared, which, as I said, would be the rest energy if it wasn't moving, and then you multiply by gamma. So we've all heard E equals mc squared. It might be better to memorize E equals gamma mc squared. And perhaps we should talk for a moment about gamma. You all know what gamma is already. It's 1 over the square root of 1 minus beta squared, where beta is just your speed compared to the speed of light. It's your speed divided by light speed. So your beta, which I call light speed, is a number between 0 and 1. You could be not moving, or you could be traveling close to the speed of light. So let's say beta can go from 0 to almost 1. Let's take a look at a Desmos graph here. Now I can't use the variable v for plotting, at least I don't know how to, so this variable x here is actually beta. X in my graph here represents light speed, beta. And this blue curve up here is gamma. So I've defined gamma of x. Think of this x really as beta. It's 1 over the square root of 1 minus beta squared. And we can see that when your light speed is close to 0, meaning when you're not moving or moving at regular speeds like driving on the freeway, gamma is basically 1. gamma doesn't really start to increase significantly until you get to, what is this, 30% the speed of light? See, if this is 0.5 c, down here would be 0.3 c, or 30% the speed of light. By the time you get to 30, 40, 50% the speed of light, gamma begins to rise very rapidly. And in fact, it has an asymptote at beta equals 1. Right? So this gamma function shoots up to infinity. By the way, gamma function also has another meaning in math. We're not talking about that. I mean gamma in special relativity. It shoots up to infinity as we approach the speed of light. And what I've done, well, I'll get to this in a moment, these other two curves here. Why was I even here? We were talking about gamma and when it starts to rise significantly. Yeah. So here's what we need next. Total energy would be kinetic energy plus what I'll call rest energy right, which we know is mc squared. So if you solve for kinetic, it's just total energy minus rest energy, mc squared. But we've just postulated, I say postulate, but I've seen this formula derived, so to speak, using the results from special relativity. That would be gamma mc squared minus mc squared. Well, let's just factor out the gamma. Whoa, where'd my writing go? Excuse me, factor out the mc squared and say kinetic energy is gamma minus 1, not to be confused with the gamma minus 1 from thermodynamics. Isn't that kind of odd? Earlier in the semester, we talked a lot about gamma minus 1, but back then, gamma was the ratio of the molar heat capacities. This is something totally different. Gamma minus 1 times mc squared. This is relativistic. Do I have to write the whole word, or can you guys just complete it in your mind? Because this is really tedious. Relativistic kinetic. This looks like it was drawn by a 2-year-old. Kinetic energy. Now, for beta much less than 1, which is true anytime you're walking or running or driving or even on the space shuttle, gamma is basically just 1. We just saw that in Desmos. It's not equal to 1. It's really close to 1. And what you can do is, I think, a power series expansion for gamma. You guys know that from calculus, right? Second semester calculus. You learn about Taylor series expansions. And if you do a Taylor series expansion of gamma around V equals 1, what you find is that the kinetic energy is very close to 1/2 m v squared. All right, so I won't take too careful of a look here, but let's look at a graph in Desmos of gamma minus 1. Go back to Desmos here. That's what the purple curve is. I just took my function gamma, subtracted 1. Let me turn off gamma here. Here's gamma minus 1, and you can see that it's almost exactly equal to 1/2 x squared. Well, remember my x is really my light speed, 1/2 beta squared, which sounds a lot like 1/2 mv squared. What I did here was assume my mass was 1, because who really cares what the value of the mass is? We're interested in how the relativistic result compares to the classical result. And you can see that gamma minus 1 only significantly diverges from 1/2 mv squared when we get to, it looks like 30 or 40% the speed of light, right about here or here. So I suppose you could just memorize that as long as your, as long as gamma minus 1, let me repeat that, or rephrase that, as long as your light speed, beta, is only 0.2, 0.3 or less than that, there's virtually no difference between gamma minus 1 and 1/2 mv squared. We'll have to keep that in mind for this problem because we're talking about an electron with a whole lot of energy. So here's the other important point that I meant to make. if your kinetic energy is comparable to mc squared, so when to use relativity? When to use relativistic mechanics, meaning 1/2 mv squared is no good anymore. We got to use gamma minus 1 mc squared. If the kinetic energy is same order, of magnitude as mc squared. Now, like I said a moment ago, Pc is not the kinetic energy. But if you look at how Pc compares to mc squared, like here's a non-relativistic, can I draw this? Whoa, particle. It's a lot harder to draw triangles here. I might have to give up here. Here's a really skinny right triangle. See how Pc is real small compared to mc squared? That particle's not going very fast. Its rest energy is much greater than Pc. You could probably get away with using 1/2 mv squared. But a relativistic particle would look something like this, right? When Pc is even greater, or greater, equal to or greater than, or even if it's like 1/2 of mc squared. Certainly here, we would need to use relativistic mechanics. Okay, let's just get into the problem and apply this stuff. So here's our overall program for solving the problem. We're given the energy of the incident photon. Let's first convert energy into wavelength. We'll find out what the initial wavelength of the electron is. Excuse me, of the photon, the initial wavelength of the photon. Then we'll use the Compton scattering formula to figure out the shift in the wavelength. If we know how much the wavelength increases by, then we'll add that to the initial wavelength to find the final wavelength. Once we know the final wavelength, we can convert that back into the energy of the final photon to find how much energy was lost from initial to final photon. So we're really just converting back and forth between wavelength and energy to figure out how much energy was given up by the photon. Once we know how much energy is given up by the photon, we can argue that that's the energy given to the electron. Find how much energy is lost by the photon, that's the energy given to the electron, and then we'll compare the energy given to the electron, which is really its kinetic energy now, to the electron's rest energy. And did I delete that number? No. So here's what I meant to get at just a minute ago here is once we know the kinetic energy of the electron, compare that to the rest energy. I guess I did say that. And if they're at all comparable, we need to use relativistic kinematics or mechanics. And yes, we are going to find in this problem that the kinetic energy given to the electron is comparable to its rest energy. Only if the kinetic energy is much less than the rest energy can you get away with using 1/2 mv squared to find the speed. So I will remind you that the energy of a photon is Planck's constant times the frequency. We use this for the photoelectric effect lab. But frequency is speed of light divided by wavelength. So the energy of a photon is hc over lambda. When you're using this formula, it's convenient to use this version of h. You can go with 4.14 times 10 to the negative 15 eV seconds. That way, when you plug everything in, you can still leave the speed of light in meters per second. The energy will come out in eV. Now in this case, we're actually solving for lambda, right? So let's flip this inside out and say lambda is hc over E. You see how if I plug in units of kiloevolts, we're given the energy, it was 350 kiloevolts. If I use h in evolt seconds, then the evolts will cancel and my lambda will come out in the units that I used for C. So I think I'll show you the result in a spreadsheet, which I prepared already, except that it's not pulled up, so give me a moment. Here's my spreadsheet. I use slightly different notation here. I'm using E0 as the initial energy of the photon, the incident photon, and down here E is the final energy. This is the number they gave us, 350 kiloevolts. The number here is what I get by applying the formula we just looked at. So if I go back to OneNote here, plug in the value of H in evolt seconds, plug in the 350 kiloevolts. At the end, I got some number times 10 to the negative 12th. Well, 10 to the negative 12th, that's pico, so we can express the wavelength in picometers, just because it's easier. 3.5 picometers. And then, in order to calculate the shift in the wavelength, the increase in the wavelength, we know that the photon is going to give up some of its energy to the electron, and that means the final photon will have less energy. That implies a longer wavelength. How much longer? Well, check that out. The increase in the wavelength is actually greater than the wavelength itself. So the wavelength more than doubles. More than half of the, I think you could say that, more than half of the energy of the incoming photon is given up to the electron. How do we actually calculate that? Well, that's the Compton scattering formula. Is it here? No. So let me just rewrite that one more time. We're using this result, that the increase in the wavelength of the photon is the Compton wavelength times 1 minus cosine theta. And remember, they told us that this photon comes in and it actually just bounces right back from the direction it came. So here's my electron. And you can also infer that the electron has to get launched in the forward direction. It can't go off at some angle because we start with no momentum in the y direction and the photon ends with no momentum in the y direction. Hence, the electron must also have no momentum in the y direction. The electron gets launched forward, the photon bounces backwards with a much longer wavelength, and this formula allows you to calculate the shift in wavelength. What's the angle that we're plugging in? Well, if something turns around completely, that's a 180 degree turn. I plugged all that stuff in here. If you take a look at the formula bar, I'm implementing the Compton scattering formula. So to find the final wavelength, we merely add the initial wavelength of 3.5 picometers to the shift in wavelength. So a little over 8 picometers is the final wavelength, and then you just go back once again to this formula, but this time solve for the energy. Hc over lambda. Plug in that new wavelength, and if you use evolt centimeters for H, you're going to get your energy out in evolts. I find that the final energy of the photon is only 148 kiloevolts. So it went from 350 all the way down to 148, which means it gave up over 200 kiloevolts of energy. Now, how much is 200 kiloevolts for an electron? You'll recall that the rest energy, this says 512, I must have rounded previously. It's something like 510 kiloevolts. That's the rest energy, mc squared, of an electron. And we see now that the electron acquired a kinetic energy that's almost half of that. So it's not greater than or equal to the rest energy, but it's still the same order of magnitude. If it's even the order of magnitude the same, in this case a little bit less than half of the rest energy, you need to use relativistic kinematics. So my point is, it's not going to be sufficient to just take that 200 kiloevolts and say that the kinetic energy of the electron is 1/2 mv squared. If you plug in here the roughly 200 kiloevolts, and you plug in the mass of the electron and solve, whoops, that's too bad. And you solve for V, you're going to get an inaccurate number. You might try it just to see how much different it is from the real answer. Instead, you need to use this formula. Kinetic energy is gamma minus 1 mc squared. What is the problem asking for? They're asking for the speed of the electron at the end. If we go back to the statement of the problem, What is the electron's velocity? Well, they really mean speed because we don't care about the vector nature. The speed is contained in here, right? Because gamma is 1 over the square root of 1 minus beta squared, and beta is v over c. So the rest you can figure out. You plug in this number. You could either plug this in evolts and evaluate mc squared in evolts, or convert everything to joules. That's always a safe thing to do. Also note that gamma is k over mc squared. In other words, gamma is 1 plus k over mc squared. So I think the easiest thing to do would be to use the number we already calculated. This is the rest energy of the electron, 510 or 511 kiloevolts. This is the energy given up by the photon, which was something like 200 kiloevolts. That's the cleanest way to do it rather than monkeying around with all these tiny numbers and giant numbers at the same time. Okay? I think you can figure out the rest. So we covered Compton scattering. We talked about relativistic energy, rest energy, and we looked at a picture of Hans Bethe's giant forehead. That will be all.